Right, so wanted to do some examples from section 6.3. So I'm going to start with number 2 on page 294 using the different rules that I showed in the PowerPoint video. So if we're wanting to integrate, so these are all given up here at the top. So we don't know what the function is. We don't know f of x, we don't know h of x, we just know this information. So the integral from 1 to 9 of -2 times f of x dx, this is that constant multiple rule. So that says that I can take out the -2 and have that times the integral from 1 to 9 of f of x dx. So then we know this is -1, so we get -2 times -1, which is 2. So here I am going to use the rule that says that functions can be added. So you can actually split this apart and say the integral from 7 to 9 of f of x dx plus the integral from 7 to 9 of h of x dx. And then we were told that this one is 5 and this one is 4. So we get 9. Then for part C, I'm going to actually use two different rules. I am going to split these apart because it is subtraction, so and integrals can be subtracted, but I'm also going to pull out the constant. So I'm doing both rules. So we end up with 2 times the integral from 7 to 9 of f of x dx minus 3 times the integral from 7 to 9 of h of x dx. And then we just will substitute those values. So the integral from 7 to 9 is 5. And then we have the integral from 7 to 9 for h of x is 4. So we get 10 minus 12, or -2. So in part D, we have the integral from 9 to 1. And we had been given from 1 to 9. So remember that when you switch the limits of integration, that just changes the sign. So we're using this rule here. So this is just going to equal the opposite of -1. So we just get 1. On part E, we want the integral from 1 to 7. Well, we know the whole thing. We know from 1 to 9, and we know from 7 to 9. So if we actually take the integral from 1 to 9 of f of x dx, and if we subtract the integral from 7 to 9 of f of x dx, we'll be left with the integral from 1 to 7. So it is kind of a play on that one where we had intervals can be added. Well, they can also be subtracted. So we end up with -1 minus 5 or -6. Then on the last one, we have the integral from 9 to 7. Well, we know the integral from 7 to 9, so it looks like that has been reversed. So we're going to take this as the negative from the interval from 7 to 9 of h of x dx, and I want to subtract and this is still from 9 to 7, so I'm going to have a double negative there, from 7 to 9 f of x dx. So then we're going to end up with, now I lost my given values. So we're going to have this first one, -4 minus a negative, so it's going to be plus, from 7 to 9 was 5, so we get 1. So that's kind of how you can use those rules when you don't know the function and you kind of manipulate those. All right, so here we are given that the integral from -3 to 0 of g of t dt is equal to the square root of 2. And we're asked to find the integral from 0 to -3. Well, we see that this has just been switched. So I get negative square root of 2. Then on part B, we're asked for the integral from -3 to 0 of g of u du. So notice it's still the same limits of integration. And if you remember when I kind of mentioned the dummy variable, it doesn't matter. G is the function. It doesn't matter the variable, whether it's an x or a t, that part doesn't matter. So this answer is actually just the square root of 2, the same as the given function. Then on part C, what's changed? Well, we have a constant. This is like having a -1 here. So I can think of that kind of like a -1. So then I can actually pull that out. And then we're just going to get negative the square root of 2. And then for this last one, notice that it's the integral from -3 to 0. And again, they've changed the variable. G of r dr doesn't matter. They've changed the variable each time, and it doesn't matter. That's what's meant by that idea of a dummy variable. I'm going to actually, this is a constant. I'm multiplying by 1 over root 2, so I'm going to actually pull that out. The integral from -3 to 0, G of r dr. So this part here is just the square root of 2, so I get 1 over root 2 times root 2, so we just get 1. So this next problem, oh, I guess I forgot to write down which problem this was. This was number, oh, it's just hidden, number 14. It says find the average value of the function y equals x minus 1 quantity squared on the interval from 0 to 3, and then at what point in the interval does the function assume its average value? So we're doing the average value of the function, and the formula for that was 1 over b minus a times the integral from a to b f of x dx. And that's how it was presented and how it is in your textbook. I tend to do it like this instead of, just because I don't know, I just like it that way, where you're dividing by b minus a. So it really doesn't matter because obviously those are the same thing. So we're going to take the integral from 0 to 3, x minus 1 quantity squared dx, and divide by 3 minus 0, which obviously is 3. And this problem said that we can use finite. Actually, if you look at the directions, it says to use finite. So we're going to do that. So we want number 4, and we're going to go from 0 to 3. And because I'm going to need to put an additional parenthesis in here, x minus 1. So be kind of careful with those parentheses, because one parenthesis is just for the integral dx. And I'm going to actually just do this answer, divided by 3, and I just used my calculator to do that. That's frightening. And so we get, the answer would be 1. So that's the average value of the function. But then the question says, at what point in the interval does the function assume its average value? So remember, the function was x minus 1 quantity squared. So now we want to say, when does this function equal the average value? So this is what we need to solve. So you can actually square root both sides. And when you do, remember, you're going to get plus or minus. So we're going to have x minus 1 equals 1, x minus 1 equals -1. So we get x equals 2 and x equals 0. And both of those are within our interval. So that is where, at those 2 points, that's where the function will assume its average value. So on number 16, we're given this function f of t equals 1 minus the square root of 1 minus t squared. We're told the interval from -1 to 1, and we're asked to find the average value of the function, but not by using finite or antiderivatives or anything like that, but by appealing to the geometry of the region between the graph and the x-axis. So this is the function that you see in blue, and remember, when we integrate, we're going to end up finding, let me change colors here, this area here. So it's between the curve and the x-axis. So we need a way, using geometry, to come up with that shaded area. So what I would do is use some shapes that we know. So I can see I have a rectangle, and this height is 1, and this width would be, or 2, or the length. So the area of the rectangle, we'll just call it that, is 1 times 2, or 2. And then we have the area of the semicircle. So if you, we know that the radius is 1. I mean, you can look at that and visually see the radius is 1. So we have pi r squared, so pi times 1, but then we only have half of that, so we get pi over 2. So then I'm looking for the whole rectangle minus this area here. I'm going to shade that in green. So I want to take the area of the whole rectangle and then subtract out the area that I have in green. That's going to leave me the part that I have in red. So that means that the actual integral, since this whole thing is above the x-axis, of from -1 to 1 of 1 minus the square root of 1 minus t squared dt is going to be equal to the area of the rectangle, which was 2, minus the area of the semicircle. And if you found a common denominator, we would get 4 minus pi over 2. So that's the integral. But remember, we have to take that and we have to divide by b minus a, so 1 minus -1. So we're going to take 4 minus pi all over 2, which was my integral, and end up multiplying, dividing by 2 or multiplying by a half. So we get 4 minus pi over 4. And you could actually take that if you wanted to on your calculator. Now that we know how to do it with geometry, you could finent this and divide by 4, and then you'll have to check the decimal approximation to show that that is the same value. Okay, so then starting with number 20, you're going to have some problems where you are just going to evaluate using the antiderivative. So this is where we're going to use the idea, the integral from a to b of f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So we're going to use that. So the antiderivative of cos, and these are all ones that you should be able to do either because they're polynomial functions or things that you just know, and they will get harder later, but not today. So the antiderivative of cosine is sine, because we know that the derivative of sine is cosine. And we're going to evaluate that at 0 and pi over 2. So we do sine of pi over 2 minus sine of 0. Top of the unit circle, sine value is 1. Here it's 0. So we get 1 for an answer. Not too bad. On number 24, we want to do the antiderivative. We're going to raise the new power by 1. And then divide by the new power. So notice, and you can always kind of write down what you think it is and then double check. If I take the derivative of this, I'm going to get 3x squared, which is what I have here. And so then we're going to plug in evaluated at 2 and then -1. So I get 2 cubed minus -1 cubed. So we have 8 minus -1, which is 9. Not too bad. Okay, so number 30, same thing. So we're going to raise the new power, or raise the power by 1. So add a power to this. So that's going to make this to the -1. And then notice I don't have to really do anything here, because if I take the derivative of x to the -1, I'm going to get -x to the -2. So then we're going to evaluate that at 4. So I have 4 to the -1 minus 1 to the -1. Remember what a negative exponent means? Flip it over, which this is just still 1. So I'm going to get -3/4. Okay, part number 32 says to find the average value of the function y equals 1 over x on the interval from e to 2e using antiderivatives. Okay, so I have to think about, because what we have to do now, we're trying to find this, the integral from e to 2e of 1 over x dx, and then we're going to divide that, because we want the average value of the function, by 2e minus e. So we have to figure this out. So you got to think, what function, if you take the derivative, do you get 1 over x? Well, hopefully you're thinking ln x. So I'm going to kind of do this separate. So I'm going to get ln x evaluated at e and 2e. So I have ln of 2e minus ln e. All right, so I'm going to divide by this in a minute, so let's finish this. Now, we can simplify this because we had some log rules, and when you have the log of a product, it's equal to ln 2 plus ln e. So you might have to review some log rules, and then we have minus ln e. So this part, my integral, is these cancel out, so we get ln 2. And then we have to divide by 2e minus e, so we're going to end up with ln 2 over, well, 2e minus 1e is just e, so our answer is ln 2 over e, and that would be the average value of the function. Then on number 36, this is the last one, find the average value of the function y equals secant x tangent x on the interval from 0 to pi over 3. So again, what this is going to look like in our notation is 0 to pi over 3, and we're going to be doing pi over 3 minus 0, or just pi over 3. Oh wait, oh, can we redo? Here, let me erase that. I'm going to do that at the end. I don't want to try and change it because I'll mess up. Secant x tangent x dx. I'm going to divide that by pi over 3 minus 0, which is just pi over 3. So we're going to take our answer and divide by pi over 3. So I have to think about what function, if I take the integral or if I take the derivative, do I get secant x tangent x? So that would be secant x. So I'm going to have secant x evaluated 0 and pi over 3. We're going to be dividing that by pi over 3. So I have secant of pi over 3 minus secant of 0 all over pi over 3. So you got to get away from that unit circle. Let's practice this. We need to find, secant is the reciprocal of cosine. So if I know cosine of pi over 3, then I can flip it over. Remember how I do mine. I know that sine, you can build a 30, 60, 90 triangle if you need to. I know that pi over 6, sine of pi over 6 is a half, which means cosine of pi over 6 would be root 3 over 2. So that means cosine of pi over 3 is a half, because they end up flip-flopping, which means secant of pi over 3 is 2. So secant of 0, actually, if we do secant of 0, let's figure out cosine of 0. So cosine of 0 is, the unit circle is 1, so you flip that over, so that means secant of 0 is also 1. So now I've got 2 minus 1 over pi over 3. So we have 1. I'm going to change this to multiplying by the reciprocal. So we get 3 over pi should be our answer. And it is. So hopefully that helps you with some of the examples or with some of the problems that you're going to be assigned from this section.